there is, for example, the approach which is also used in this lazy sampling methods, where instead of providing edges in your roadmap, you accept also paths which intersect obstacles. This is shown also on the slides, where suddenly a path goes through the obstacle, and then you couldn't call it really an edge, you call it a segment. And when you finish, you have to fix basically the roadmap just by pushing the path outside of the obstacle. So in the end, the third and the fourth way of improving connectivity of probabilistic roadmap is the similar. You try to really find points along the boundary to guide the path along the obstacle. So this was basically 4 ways how to improve connectivity of multiple query. Now for the single query, you need to understand that things are evolving. So the paper from Latom, which introduces the bidirectional single query map, single query trees, is basically an extension of what you read in the book. So instead of having a single tree expanding from a point, you just basically implement the idea that you may not need the entire space for sampling. Let me just put maybe, I need to make myself presenter here, I guess. Which one is which? The presenter, okay. Presenter. So basically what you have here is some configuration space, and usually what may happen is that your start and your endpoint may be really in some local neighborhood of the entire space. So the idea of this bidirectional single query tree is basically to make sure that you don't expand into spaces which are not really necessary to solve the task. To make this possible, like if I would extend the tree, if you would think that with each step, just for some intuition, if you think that in each step you extend basically kind of a concentric, this works. This is something I don't want. How do I say no? Here, okay. So basically you see, if I would grow the tree just from one point, I would extend basically my nodes to the region spanned by this red obstacles. If I do the bidirectional tree, at the same time I will be starting extending a tree from the other side. This is wrong. Just a moment. No, go away. Yes. And you see, after this expansion on both sides, I suddenly start having nodes which are close together to connect. That means extending the single query tree from the way it was initially implemented to this bidirectional tree just additionally reduces the number of the space I'm exploring, which may be unnecessarily sampled. So in the end, for the lecture, I basically kind of stick with this bidirectional tree from Latom, and this is basically something which efficiently samples through the space. And for single query, there is no lazy approach, because you don't place sample everywhere. You just extend from the trees. if you have a multiple query tree, a multiple query probabilistic roadmap, let me just try to draw it one more time here. Configuration space, some obstacle, now some node, one node, sorry, circles are not. So these were the two nodes that I'm connecting. And now if I'm trying to generate an edge of the graph, what I'm, sorry, I need to do the line. What I'm trying to do is building this connection. And of course, this intersects the obstacle. So without the lazy implementation, this is not a valid edge for such a map. But I can accept it as a segment and later just push basically this segment outside of the obstacle and try to fix basically the resulting roadmap. Let's just try to see if I can do it freehand to something like this. So this, as you can imagine, this helps me to deal with narrow passages relatively good, because by accepting this segment, I'm already now switching to the desired behavior that I want to sample along the boundary. Sampling along the boundary, as was shown in this obstacle-based probabilistic roadmap, is basically a way to solve the narrow passage problem. The problem with obstacle-based probabilistic roadmaps is the coverage. We talked about this last time as well. The coverage is not really great because the samples are not uniformly distributed in the space, but usually grouped around the obstacles. So that's for the thing. Like for the lecture, basically stick to the slide. For the exam, stick to the slides. PRM with the 4 types of extensions: increasing points, random walk, obstacle-based place, obstacle boundary node placement, and this lazy or proximate path solution, which I just shown here on the screen. And for single query approaches, an efficient method to do it is not to extend the tree just from one point, as you see on the right example, but really start with this bidirectional Fermat hump, where you extend 2 waves basically, and they meet a lot sooner than waiting for one wave to sweep through the obstacle. So this could be kind of the. And the last question in the email was RRT. I said that RRT is starting from one point. According to book, it seems RRT can also be applied for 2 trees. So sure, you can apply this. RRT is just basically a procedure how you sample the space. And in RRT, the difference is that we accept basically. So in the PRM method, multiple query PRM method we discussed in the class, I was throwing away solutions which were going. So the typical part PRM would not be able to connect these 2 nodes. So if I have 2 samples on 2 sides of the obstacle and the direct line connection fails, this is a no-go. What RRT is doing in this case is would also sampling just these 2 points, and would accept basically an edge which goes from the already connected node all the way to the boundary of the obstacle. So the difference is here slightly how I handle connectivity between the nodes. So just imagine that what you see here is on one hand different ways to sample the space, and now of course you can also play optimization methods to reduce the number of nodes you can apply and to maybe reduce also unnecessary sampling through the space. So I hope it kind of a little bit explained what's the differences between what you see in the book. It's always like this, you know. Printed books, of course, are not always representing the newest things which you apply in this thing. So I just wanted to show you how to extend it. Now let me just go back to the questions here in the public chat. Slide 16, lecture 8. Observability is necessary to let the Kalman filter work well. Okay, so so this is now about the Kalman filter. I hope you understood now where it's coming from. What we discussed until now were some knowledge about the obstacle, where we may have not inspect the obstacle, but we knew that the obstacle, but we had an accurate knowledge about what it is. And the same thing was true for the robot. So let me just draw a small example here. What we have here is obstacle, robot. So what we assumed is that we know at any point in time we can assume absolutely accurate where they are, but it's never the case. So what usually happens is that we have some uncertainty. I should use a different color. We have some uncertainty in the position of the obstacle, and we also have some uncertainty in the position of the robot. And now the Kalman filter is trying to use different inputs about the information we try to observe to have an optimal fusion. So Kalman filter is an optimal fusion framework for the case where the noise in your observation is Gaussian and zero mean, and where the transition between consecutive observation can be described as a linear combination of the state parameter. And for this optimal case, what we have is, don't be surprised, I'm coming to the answer of the question now. What we have, let me just try to write. What we always assume in a Kalman filter that we have some state X from K. So this is basically the time step. We have here a discrete Kalman filter, which is doing steps. And now we can have, let's say in a one-dimensional case, we can observe X, for example, and V, or X dot. So let's say the simplest, this was wrong, let me just try a line. The simplest observation is we have a robot walking along the line. The robot is somewhere here, and it can be described, the state of the robot could be described now by X and V, by its position and by its velocity. And now the question is, what observations do I need to provide to the Kalman filter to keep it convergent? As you may have seen on the slides, we have not only the state, but we have also, let me just go back to the right thing. We have also the covariance of the state, P from K. And the covariance is basically this ellipsoid here, for example, in my drawing, where I have some uncertainty. So if I would repeat a measurement of my robot position multiple times, it is due to the error I make during the measurement, I would have a spread of this measurement building a two-dimensional Gaussian here in the space. And if I try to transform it into the next state, what I get is a state transition matrix P. Why is it not writing? Something went wrong. Maybe my keyboard was just sleeping. A, P, A transpose. This is supposed to be transpose, so I'll put a small t plus Q. Great. I need another box to put the Q. I hate this tool. Which we know. Q. So if I want to actually progress to the next timestamp, I get this Q. That means if I would run my Kalman filter purely on prediction, just propagating the state, my covariance would be, of course, propagated with the state transition matrix to the next state. So this expression would just make sure that the Gaussian gets projected correctly into the output space, but will not increase the uncertainty. The uncertainty in my definition gets increased by the Q, by the system, by the model error, system model error, and this makes it basically, this makes Gaussian to flatten. So if I'm running now a Gaussian here on my robot here on the top, let's just switch to some ugly color. I have, this is supposed to be Gauss. I have some Gaussian from the state K. Now my robot moved to a new position somewhere here. This is my K plus 1. And now without this Q, the Gaussian would stay the same, but the Q, the system model, adds uncertainty to my prediction and makes the resulting Gaussian, okay, it's supposed to be lower because the area under the Gaussian should always be the same. So of course, if it's flatter, it's also lower. Drawing is really not easy. So the Q flattens it. That means just prediction steps are not enough in the Kalman filter. I need to include the measurement. And now the question is always, what do I need to measure? And many people are not really checking the observability, which is the question here. The observability is just telling me if I provide enough input information to my filter to keep all state parameters from diverging, from flattening out the Gaussian. If I don't update the information of some state parameter, then the corresponding Gaussian would just flatten out. And flat Gaussian just means, well, I give you a value, but any other value has the same probability to be true. So the observability metric H equal to just upload the slide maybe. What's the H? H is H. Now I know why I get lost. It's the, of course, the observability matrix is O. This is supposed to be O. Is equal to the first one is the measurement matrix. Right. The second entry is H A. It's the measurement matrix times the state transition matrix all the way to H times A to the power n minus 1, n being the number of parameters of my state vector. So only if the observability matrix has the full has a rank of n, line rank of n, then my system is observable. for the example of this x and v, it's still it may be still relatively easy to see if I observe it correctly or not. But if we have strongly coupled parameters in the state transition matrix, it may be not really obvious if one of the parameters is still observable or not. You don't need to measure all the parameters of the state. You can measure, for example, just x, and measurement of x also gives an update of v, just because x and v are coupled in the state transition matrix. But as you learned from the slide, hopefully, measuring just the v gives you the case where the observability matrix does not have rank m. And in this case, one of the parameters will flatten out, and the parameters which will flatten out in this case is the x, just because small error in the x will never be corrected. There is no observation which would update the x, only v is updated in this case. So the observability matrix is necessary to let the Kalman filter work. It would just diverge. And just I think I mentioned at least 10 times in the lecture, people are abusing Kalman filter for things. So Kalman filter should be only applied if you have a linear state transition. So basically, if the A matrix is just basically a numerical matrix, so if there is a linear relation between the previous state and the next state, the second condition is that you have to have a linear relation between the measurement and the state. The linear relation is with the measurement matrix H, which was also here. And the last two constraints is that you have to have Gaussian error in the state, and you have the Gaussian error in the measurement. This is often violated by papers. So this is where you should be starting using. And what you see often is that people start with a Kalman filter and then just trust the output of the Kalman filter without ever looking at P. And this is really the danger, because the Kalman filter, which will always output you some number, only checking the corresponding covariance tells you if you can trust the number or not. If the P entry in your matrix becomes very large, this just means the probability of being where I'm telling you I am is maybe as good as being anywhere else here. So that's why if you don't check observability and you don't check the covariance, like if you don't check the covariance, you may be using values which are just not really trustful. And if you check the P and notice that the P is diverging, the reason for this could be that you did not check the observability, and that some of the values in your parameter space are not observable. So regarding lecture 8 in slide 13, there are two approaches to model the same system. The first is to include parameters in state vector x, for example, velocity. Parameters when trying. Yes, so it's basically